Okay, good morning. All right, so let's talk about the exam. The results came back. Thank you. Okay, let's talk about the exam. The results came back. Um, you should see your score on Web and Science soon. Now, we had some technical difficulties with getting the score from one place to another. We're looking into that. If you haven't seen yours yet, it will be there soon. The average is 72, which is very good, by the way. So congratulations on doing such a great job. The cutoffs are 90, 80, 60, and 50. Once again, let me remind you that these cutoffs are just for the exam. It does not mean that you're going to need a 90% at the end of the semester to get an A. But if you can maintain the 90% throughout the semester, your chance of getting an A is really, really good. Same thing goes for B and C and D and so on. About D here, if you have been getting below D on the two exams, we need to talk about what's going on and see what you can do to get yourself from the low range to higher up. Okay? That's the exam. Okay, today we're going to look at section 11.3. For most of the sections in this chapter, we're concerned with finding out whether a series converges or not. So first of all, let's review what we already know. We saw the geometric series last time. It's a very nice series. We can tell right away if it converges by looking at the common ratio R. Then we can find the sum, right? So what has to happen for a geometric series to converge? Right, that the absolute value of the common ratio has got to be strictly less than 1. That also means R has to be between minus 1 and 1. Strictly. It cannot be equal to 1, cannot be equal to minus 1. What about the sum? Right? A over 1 minus R, right? The first term over 1 minus the common ratio. So that's the geometric series. Very nice series, easy to check, and easy to find the sum. Unfortunately, most of the series that you will see in application are not as nice as geometric series. It is often quite difficult to check convergence and also quite difficult to find the sum. Now today we're going to introduce one method to test convergence called integral test. By the way, before we even talk about that, you're going to learn a bunch of different tests from this point on. The first one you always want to use right away is to check if the terms go to 0 when n gets large enough. If it doesn't go to 0, then right away we know the series diverges. So you stop even looking at that series. There's no point looking at it anymore. There's no sum to talk about anymore. Okay? What does it mean if it does go to 0, though? Does it mean it converges? No, it means that it might converge. It means that there's a chance for that series to converge. So there's reason to look into that series a little bit more in depth. Okay? So be careful. This is what's called a necessary condition. For a series to converge, this has to happen. But it's not a sufficient condition. This alone happens is not enough to guarantee a convergence. It's necessary, but not sufficient. So let's look at how the integral test works. We'll start with this series. It's a pretty simple one. 1 over n squared. It's 1 plus 1 over 4, 2 squared, 3 squared, 4 squared, 5 squared, so on and so on. Okay? So remember, first thing to check, you want to see if this thing eventually go to 0, and quite obviously it does. So now this is saying that a series has a chance to converge. It still may diverge. Think about the harmonic series. The harmonic series has this going on, but it diverges, right? Now let's look at this series here. I'm going to graph this in this way. The series is determined by 1 over n squared. Now again, we're going to imagine that the series comes from sampling a function at selected points. So 1 over x squared is what's going to give me all these values. Okay? At x is equal to 1, notice that the first term, a1, the first term here, is represented by the area of that rectangle under the curve, using the right endpoint as the height to form a rectangle. Right? You see that? Same thing happens with the second one. Right? And the second one here, the height is 1 over 2 squared. So the height is 1 over 4. The width, of course, is kept at 1. So 1 over 4 can be interpreted as the area of that rectangle, this rectangle right here. And then this pattern continues. This right here is 1 over 9, right? And then so on and so on. This is 1 over 4, 1 over 5, And of course, that continues. Now let's look at this thing here. Notice that if I add, well, first of all, if we momentarily ignore A1, the first rectangle for now, if I add up A2, A3, A4, A5, and so on, so if I keep adding all of these up, we're looking at the area from here on. Notice that it's no bigger than the area under the curve, under this curve. Do you see that? It's no bigger. It's got to be smaller because we have these areas unaccounted for. So what we can write here, actually let me rewrite this one here. Sorry about that. Let's write as A2 plus A3 plus A4 plus dot, dot, dot. Whatever this turns out to be, we know it's smaller, but at most, equal to the area under the curve. And the area under the curve is starting at x is equal to 1. Where does it end? Infinity, right? It keeps going. We're not stopping anywhere. Okay? So we're saying that all of these rectangles added together, which represents 1 over 4 plus 1 over 9 plus 1 over 16 plus 1 over 25, blah, 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 is no bigger than this. Now, do you remember if this improper integral converge? We did that 1 over x to the p thing, remember? And back then we said that if the power is bigger than 1, this would converge. So this does. Okay? If you forgot that, you can simply just integrate that the usual way with improper integral, and you come to this result. So if this converges, then A2 plus A3 plus A4 all the way to AN converges too. And that means it has a fixed finite sum. And now when I add this back on there, it is still a finite sum, right? So what did we find out? When did I switch to black then? Back to blue. I like blue. So therefore, by adding another finite number to an already convergent sum, right? So all of that is a finite sum. Adding a finite number, that's another finite sum. And this is what we were looking at in the first place. So therefore, that series that we were looking at 1 plus 1 over 4 plus 1 over 9, blah, blah, blah. That converges. Okay? Okay, so does that basic idea make sense? Yes? Okay, we treat the series as a bunch of rectangles added together. Compare that to the area under a curve. If the curve gives me a convergent improper integral, then the picture shows that we're adding up rectangles that are smaller than a convergent improper integral. Therefore, it must be a convergent series. So the important thing here is, if something is smaller than or equal to a convergent improper integral, then it must also be convergent. Right? Convergent improper integral means it's a fixed finite number. Something strictly smaller or equal to it has to be convergent. What about if I add up a bunch of things and it turns out to be bigger than or equal to a divergent improper integral? What's the conclusion? What does it mean when the improper integral is divergent? What do you get out of that integral? Something that's blowing up. So something bigger than that is also blowing up. Right? So that's the basic idea of the integral test. We're going to look at a series treated as a sampling of a continuous function integrated. If the integral is divergent, then the series is also divergent. If the integral is convergent, then the series is also convergent. Yeah. Less than or equal to. Right. It actually does. Let me show you what's going on here. Well, let's check it out. It's sort of tricky here. Okay, so we just saw that we have two ways to represent these series we got. Actually, we saw this one way. I'll show you the second way. So that's one way to look at it. Right? So we're saying that the series the series here is less than or equal to the first one plus the integral under the curve. We just saw that. So if this thing converges, then series diverges. Right? We just saw that. Very simple. Now what happens to the divergent case here? Just checking, see how awake you are, and how awake I am. I am awake. Okay, convergent, converge, right? This is a very simple thing. If the improper integral converges, that's what we do. That's how we represent a series. Therefore, it converges. But we could also use the other endpoint to represent our series. Right? So for example, I could go to x is equal to 1 and use that height here, and then use the left endpoint to represent my series. So this will be A1. And this will be A2. And this will be A3. Right? You see this? Adding up these rectangles here give me the same series sum. But in terms of comparing to integral, it's slightly different. So now what we're seeing here is that my series A1 plus A2 plus A3 plus dot, dot, dot is bigger than or equal to an improper integral from 1 to infinity f of x dx. Right? Because the rectangles are poking out. So my series sum is bigger than that. So if you can determine whether the improper integral converges or diverges, since both of these ways are the same way to represent a series, if we know what this is doing, then we can make a conclusion about what the series is doing. No, you're talking about the sum, right? The sum is not the same. Okay, we've got to be careful. This tells you, that's an important point, actually. This does not give us the sum. It tells you that there is a sum, but we cannot make any connection between the sum and the area under the curve. We use it to determine the convergence, and that's it.
Like whether or not it is converging, always the same as the integral?
Yeah. If the integral converges, series converges, because we got the top case here. If the integral diverges, then we got the second case here. The series also diverges.
So just to clarify once more, both of those sums can be described by the same series?
Yes. Both of these rectangles, these set of rectangles, right? If I add 1, 2, 3, 4, and 1, 2, 3, 4, I get the same value, right? So, but which way I choose to represent it is up to me. And why I can decide which way to represent by whether the series converges or not. If it converges, I'll choose this one because my sum will be smaller than the area. Therefore, it converges. If I find out the series, the integral diverges, then I'll choose the second way to represent it. And since my rectangles are poking out, it's bigger than infinity, then it must also diverge. That's a good point, because I'm about to write down the technical description of the test. We must have a function that's positive and decreasing. Okay, so let me summarize that. I was about to do that, but you brought it up. Good point. Okay, so here's what this integral test says. a positive and decreasing function such that f of n is equal to an. In other words, that's where we get the series from. We sample this function, and at selected points, we grab out the numbers, terms in the series. Okay, so these are the important requirements. Must be a positive function, like the cases we saw earlier, and has to be decreasing. So this is the necessary ingredients for this test to be valid. If you come across a function that's not positive and not decreasing, this won't be good. And then the series will diverge if the improper integral diverges. It converges if the improper integral converges. But this test, be very careful. We can calculate the integral and all that. It has nothing to do with the sum. We can't infer very confidently what the sum will be. We can probably narrow it down, but we don't know what it is, and that's a different thing. This only tells us if the series is convergent. In other words, if you want to find the sum of a series, you got to find out whether it converges first. If it doesn't converge, then the question is meaningless. If it does converge, then you go ahead and find out what the sum is by various means. You could be looking at the partial sums and then try to find a limit that way, or some other ways. But the question that we're focused on right now is the convergence question. Okay, let's do a few examples. All right, 1 over the cube root of n. What's the first thing we got to check? Right, before we do any of this, we got to check this. If it doesn't go to 0, then this thing will certainly diverge. If it does go to 0, then this may converge. Then we look at the integral test. Yes? No? Does it go to 0?
Yeah.
Pretty clearly, yep. Yes. So it might converge. Okay, now we got to check further. When I calculate the improper integral, it turns out to be convergent, then the series also converges. Oops, that's an X. Right. Okay, so now we're going to calculate the improper integral. Yank out the infinity, put an a in there, and let a go to infinity, and then we calculate what we end up getting. Add 1, I get 2/3, divided by that, 3/2, 1a. So we get 3/2, a to the power of 2/3 minus 3/2. Right, and what do we get? Infinity. Pretty clear. All right, so this is like the second case here. I found out that the curve, the improper integral is divergent. So now I'm going to choose to represent my series this way and say that these are poking out, and therefore the sum of my terms in the series must also be divergent. Since the improper integral diverges, the series diverges too. Questions? Yeah. Actually, yeah, it would make sense to check if what is decreasing, but it is decreasing. So you're right. We actually do technically have to check if this is a decreasing function. And you can graph a few of these points and to see that it does decrease. So you're absolutely right. Thank you for bringing that up. It does decrease, and technically we do have to check. Okay, the functions I'm going to show you today are all decreasing functions, but he brought up an excellent point. Okay, let's change that power a little bit. Instead of the cube rule, let's do cube and cube. Again, check if the limit of that goes to 0. All right, so it does not diverge. That's what it says. Does not conclusively diverge. Well, let's take that back. That's too strong a statement. Has a chance to converge. There we go. Now, you can't say it does not diverge because it means it does converge. There's no midway between converge and diverge. So it has a chance to converge. Always think about the harmonic series when this happens, but it still diverges. Okay, now we just got to integrate this. 1 to infinity, 1 over x cubed. We've done this many times. And what do we get? We get minus 1 over 2x squared, 1a And when a becomes large, this first term goes away, and we get a 1/2. Okay, so the improper integral converges. Therefore, the series converges. All right, so compare this to the last one. The difference here is this power downstairs, 1 over n to a power. And as you can see, there's some number between 1 and 1/3 where the behavior changes. Care to guess what that number is? 1, yeah, just like the improper integral we did before. 1 is the dividing number. So that's sometimes called a p-series test. And it's a consequence of the integral test, that's all. But so what this says is that the infinite series 1 over n to the p converges if p is greater than 1. Anything less than 1 or equal to 1, the series does not converge. What do you get when p is exactly equal to 1? What series comes out? Harmonic, right. Okay? So that's the p-series test. Anytime you see a series of that kind of form positive, then you can use this series. Just simply look at the power, whether it's bigger than 1 or not, and then you can decide what's going on. Let's do another example. Okay, let me give you 2 minutes to answer that question. Find out if this thing converges. May not even need 2 minutes, but take 2 minutes. Okay, closing after 2 minutes. Converge or not? Does not. Raise your hand if it converges. Raise your hand if it diverges. Good. That's what I wanted to see. So what's this? What's the general summation notation thing we're looking at? 1 over n cubed, right? Okay, so by the P-series test, this is evident. E greater than 1, so it is converging. Wow, that's easy. All right, so now let's talk about the sum, right? Once we've established that this thing is convergent, then the next question is, what is the sum? This is not a geometric series, so we can't calculate the sum very easily. But what we can do is to use the idea of the integral test to set a lower limit and an upper limit of the sum. So let's use S for the total sum, and the nth partial sum is 1, A1 plus A2 plus A3 plus all the way up to AN. Okay? So notice that the total sum here is equal to the partial sum plus some remainder. Right? If I use the third partial sum to try to estimate that, then this is A1, A2, A3, and everything after that is the remainder. So this, well, let me write this out. This is going to be A1 plus A2 plus dot, dot, dot to AN. So that's S plus AN plus 1 plus AN plus 2 plus dot, dot, dot. And these guys are the remainder. Those guys combined, we'll think of that as the remainder. So now we're going to use the idea of the integral test to try to trap the value of Rn. Once again, for a decreasing and positive function, all of these things can be looked at in two ways again. So this is AN plus 1, AN plus 2, and so on. Right? Just like using the integral test, I can represent the remainders this way. Or I could choose to represent the remainders this way. Okay? Just like using the integral test. So what this is saying to me is all of these remainders, when I add them together, it's got to be somewhere between integral from here to integral from here. One is smaller, one is bigger. Oops, I missed my arrows. my God, what am I doing? So this is an plus 3, sorry. So because I'm using the right endpoint, the first rectangle is representing an plus 1. That's the height. So once again, if I integrate from n to infinity, then my remainder must be smaller than that. But if I integrate from n plus 1 to infinity, my remainder must be bigger than that. So in essence, I've trapped the possible range. I trapped the remainder in a possible range. So therefore, what we see here is this is how we trap the remainder. I integrate from n plus 1, and that's the lower bound of my remainder. And I integrate from n to infinity, and that's the upper bound of my remainder. Okay, now let's answer the second part of that question that we didn't ask earlier. We found out this is convergent. Now let's find out the sum of that series. Let's estimate 1 plus 1 over 8 plus 1 over 27 plus 1 over 64 plus 1 over 125 plus dot, dot, dot. One, two, three, four, 5. I have 5 terms here. If I simply add up the 5, then that's my 5th partial sum. So this is about 1.185662. But then the true sum is what I just got plus the remainder from the 6th one and so on and beyond, right? So now I can use this to figure out how big this can get. The left hand, the lower bound is integral from n plus 1. We went up to 5, so we start at 6. The right end is starting at n. And it's 1 over x cubed because this is 1 over n cubed. Okay, and I calculated these two beforehand, and these are 0.013889 and 0.02. So this is the range of what I have thrown out of this series. So therefore, my sum must be between this plus that and this plus that, right? So that gives me the true sum of 1.199551 to 1.205662. And what do you think is going to happen if I use a higher partial sum? What happens to the range of remainder? It gets smaller, right? If I could actually go to infinity, this will eventually vanish. But the bigger the n, the smaller this range is. Therefore, the better your sum estimate is. This is pretty good here already. We know it's got to be somewhere between those two. 1.2 is probably a good enough answer. All right, that's it for today. See you Friday.